try to discuss what are sort of the interesting open questions in fracton physics. We were supposed to have 3 panelists, but unfortunately Mike and Meli couldn't make it, so we're going to have Nadi Seiberg and Yizhi You. And everybody knows Nadi and Yizhi before, so I don't think we need any great introductions. And then the 2 panelists are going to give like short presentations first, and then we're going to open up the discussions for the Zoom and the in-person audience. Go ahead, Nadi.
Thank you. First, I want to thank you for inviting me to speak here and putting together this conference, which is quite exciting. I was asked to talk about interesting open questions on fracton phases and share with you my view of the subject. And my view was shaped mostly in conversation with these 3 people. I believe they are either in the audience or they've already skipped down. So they could also represent the views I'll present here. I also want to use this opportunity and thank them for keeping me sane during the pandemic, which will look just like you see in front of you. Before I start talking, I'd like to slightly change the title of the panel, if Andreas helps me, and make it a little bit broader and say interesting open questions on exotic models. And I think this is a broader question, and fractons are just one example of many interesting models. I'll soon enumerate them. And I'll try to highlight why I think they are interesting and what the possible directions for future research in them are. So what are these exotic models? There are many known ones, and they fall into different categories. And new ones are, we keep discovering new ones. So the first class, this is not a complete list, is Lifshitz theory. And there are many references. And the code will be that this green color is references, and this brown color will be used for references to this conference, this mini conference. So we heard a little bit about it in Son's talk this morning. This is Lifshitz theory, which is a higher derivative theory. There are also other theories with different structure of the derivatives arising from the lattice. These are the XY plaquette model of Paramakanti et al. With a lot of followers. And then there are various fractal models, starting with the pioneering work of Shamon, Ha, Vijay Ha, and Fu, and lots of others. And there are many other examples, and new ones are being discovered. And so the list is not complete. There isn't a complete classification. Some of these models are gapped, some of them are gapless. Some of them have some peculiarities, others have other peculiarities. And I'll soon mention some of these peculiarities so we'll know what we're talking about. One problem or one challenge with these models is that all of them do not fit the standard dogma of lattice versus continuum quantum field theory. The continuum quantum field theory that if we just follow our nose and write a continuum quantum field theory, it turns out to be extremely subtle. And we saw some of that in the discussion in Son's talk this morning. But also the relation between the lattice and the continuum is not straightforward. So this is one big challenge. And this challenge you can trace back to where it comes from. And this challenge really comes from the peculiar features they have. So let me enumerate some of the peculiar features and the questions that they lead to. The peculiarities like funny ground state degeneracy, various singularities that we do not expect, particles with restricted mobility, and so forth. But one problem we have is that not only don't we fully understand these peculiarities, we're not even sure whether they are related to each other. So is it the case that if we have one peculiarity, we should also have the other? That's sometimes the case, and sometimes is not the case. It's also challenging how to think about these theories. We have a framework how to think of lattice models and the corresponding continuum theory that describes the long distance behavior and the phase transitions between them. This dogma does not work here, and I'll soon explain in more detail what I mean by that. But you could say maybe the dogma is not right, we don't care, or maybe the dogma is irrelevant here, but there's still a question how to organize these theories. And normally we organize theories by their phases, the long distance behavior. We characterize the long distance behavior by some continuum field theory or some order parameters or whatever language you prefer. And that gives us some kind of a classification. We don't have a corresponding thing for these models. In fact, we don't even know what the right order parameters are. And not only do we want that, we would like to have classification, not because we would like to have something like a telephone directory classified, or stamp collection, but instead we would like to have classification in order to understand whether there are new examples, whether we could prove theorems or prove results in general for classes of them, but not for others. And as I said, the most promising framework is to follow the framework that has been successful for decades now in using the language of quantum field theory. But this doesn't quite work, because if we follow our nose and write down the continuum field theory description, namely we assume that the nearest neighbors are close to each other, or if these are discrete variables, we look for an order parameter and we try to write down the Lagrangian with a small number of derivatives, we get Lagrangians whose results are very puzzling. And again, we saw that a little bit in Son's talk this morning, but that's also true in the other cases. So we should ask ourselves, what do such continuum quantum field theories even mean? If you take your favorite continuum quantum field theory textbook, it does not address these kind of models. So what does it mean? And one aspect of it, which is funny, is that if we just write this Lagrangian and we think of it, take it literally, we see that we must consider discontinuous field configurations. It's not up to us to decide which configurations are included and which not. We just look at the equations of motion. And typically, discontinuous field configurations have infinite action, and therefore we don't have to discuss them. That's not the case in many of these models. The field space is also subtle, and it has global features that could be quite confusing. And we saw some of that in Yizhi's talk earlier in the conference. This came up, and also in Son's talk this morning. And I feel that these global issues are not just quantum field theories being picky and try to understand the space of functions a little bit better. They are actually quite significant, and they're really central in recent developments in condensed matter physics. We should really be paying attention to that. And related to that, we need a more precise understanding, a more complete relation between the lattice and the continuum. Because as I said, the lattice model clearly makes sense. The continuum theory is puzzling, so we need to understand how to relate the two. And I believe that if we understand that better, it will also give us better understanding of quantum field theory in general. And if these models are outside the framework of standard quantum field theory, it's even more of an impetus to study them, because this thing is a win-win situation. If it is within quantum field theory, we'll learn something new about quantum field theory. And if it's outside, the prize will be even bigger. For some reason, this whole set of questions was not present in the quantum field theory panel. I don't know why they decided that that's not something that should be mentioned, that quantum field theory might not be the full story. Going through the common feature of these models, all of them can be traced back to one thing. So I'm trying to find, is there any relation between all these models that are so different? And one thing that they all have in common is that if you look at the low energy states, there are too many of them. And the system could be gapped or gapless, and it could have this ground state degeneracy or another. But the characteristic feature is that there are too many low energy states to be described by a standard quantum field theory. Related to that is the issue of UVIR mixing. This is long distance physics being sensitive to short distance details. This goes against the picture of the renormalization group. It goes against the picture of universality. And there have been some suggestions in the literature how to address it. But let me say a few words about it, because this is a topic that is really close to my heart. There are several different manifestations of this UVIR mixing, and not all models have all these manifestations. There's a large ground state degeneracy that depends on the number of lattice sites. So if it depends on the number of lattice sites, this is clearly a UV detail, which shouldn't be there in the continuum limit, or even if we take the number of lattice sites to infinity, and yet the number of ground states depends sensitively on the number of sites. Related to that, there are subsystem symmetries. these are symmetries that the symmetry group element depends on the number of lattice sites. Even the size of the symmetry group depends on the number of lattice sites. This is not common in quantum field theory, and this was discussed in detail in the generalized symmetry panel. So I will not go into detail here. Related to that, if there's a symmetry operator that is different at different point on the lattice, there are correlation functions that vary on the lattice scale. So if we move the observable a little bit from one side to the other, even in the long distance theory, the correlation functions could change. This is clearly a UVIR mixing because we are interested in the correlation function at long distances. So we take X very big and we change Y a little bit and the correlation function could jump. Related to that is that in some of these models, we can take L to infinity in two different ways. In fact, there's more than two, but two simple ones. One we can call the continuum limit. This is removing the UV cutoff, holding the size of the system fixed. And the other can be called the thermodynamic limit. We take the number of lattice sites to infinity, making the system bigger and bigger. Here, we remove the UV cutoff, staying in finite volume. Here, we remove an IR cutoff, keeping the theory on the lattice. In normal systems, these two limits commute, and they should commute because they're usually sensitive to different things. The infrared behavior and the ultraviolet behavior are unrelated. That's not the case in all of these models. These phenomena were mentioned, or at least alluded to, in the quantum field theory panel. Let me say a few more words on the large symmetry group. Historically, and going after the symmetry group has been a very powerful tool in analyzing models. That goes back to early days, even in the 19th century, but in the 20th century from the work of Wigner and others through the standard model of particle physics, Landau paradigm, etc. Here, the symmetry group is very, very large. As I said, it depends on the number of lattice sites. And we found it convenient to separate the symmetry transformation to space-like and time-like. I'm not going to elaborate on this here. I will just say that what we normally call symmetry is the space-like symmetry, and it organizes the states, and it underlies the large ground state degeneracy. The large ground state degeneracy is there because it is a representation of the space-like symmetry. We also introduced a notion of time-like symmetry that acts only on defects, and it underlies the restricted mobility of these particles. This statement is extremely satisfactory because these models have two peculiarities: large ground state degeneracy and particles with restricted mobility. And we can have models with one of them, but not the other. We can have models with both, and we can have models with neither. Now we see that both of them are controlled by symmetries, but different symmetries. And this symmetry group could even be different as a group. So they are really two different properties. Both of them are controlled by a symmetry. So both of them are symmetries, but they are unrelated. So this topic that there is a very large symmetry, but it could be either space-like or time-like, could have been discussed in the generalized symmetry panel, but for some reason it wasn't mentioned. Since this is a panel discussion, I have a few more minutes, I'd like to speculate about my vision for the future. What do I think the future would look like? What will conferences like this discuss in a few years in the future? So I believe there will be many more examples exhibiting new phenomena. I think what we have seen is only the tip of the iceberg. The examples that were found by accident. And as people keep searching, there will be new phenomena with new models. In fact, I can advertise that the group of 4 of us that I showed earlier are writing papers now with many new models, with new phenomena that had not been seen before. I think that with more examples, a pattern will emerge. At the moment, I don't see a pattern. And honestly, this classification into type 1 and type 2 and maybe continuum, I think this is too simplistic, and the proper classification will be more interesting. Being more speculative, I think that there will be new insights about the relation between the lattice and the continuum. The continuum is supposed to capture the universal properties of the lattice, things that are not sensitive to what happens at short distances. I think that we'll understand that a lot better, especially here when we have UVIR mixing. I think that there would be new global symmetries, and we'll use the global symmetries as the organizing principle. Question appeared in one of the earlier panels, forget when, whether this is important or just a technicality. I believe that this is an absolutely crucial part of the story, and we'll organize these models based on their symmetries. I think there are some extent we'll need to go slightly outside the framework of standard quantum field theory, because there will be some notion of an underlying lattice that will have to be kept, because otherwise the ground state degeneracy is infinite. And all that, I think, will lead to some new insights, even about standard quantum field theories that are more well-behaved and are more standard. So this is my speculation for the future, but I'd like to make two more comments about the future. What we're doing here is playing mathematical games. There's this model and that model, and it has this ground state degeneracy on the other. Since we're doing physics, we shouldn't forget that it would be fantastic to have experimental realizations of these systems. We have something that can be done in the lab, even if it captures only the absolute simplest system. I think experimental realizations will be fantastic. And if they exist, we can even envision some technological applications, better memory chips and so forth. So I'll end this talk by saying there's a lot of work, and let's do it. Thank you.
Thank you. Maybe if there's some urgent questions directly to the talk, you can ask them now, but probably we should have both talks before we go into more like conceptual questions. Do you see anything online, Yale? No, okay, then maybe we ask Yizhi to give her presentation, and then we kind of have a more open discussion.
Okay, thanks. Okay, so I'd like to thank again for all of the organizers for putting up this wonderful workshop and have a special panel discussion about what we know about fracton, what are the opening questions, and what are we expecting in the future. So because I remember up to this point, we already have several 3 to 4 talks on fractons, and I don't need to give any introduction on that. And during the past few years, what we know about fracton, historically, it was proposed by some exactly solvable models from HA and VJ, where we know that they have a gapped, well-defined quasi-particle that contains restrict mobility and exotic ground state degeneracy that do depend on the geometry and do depend on the spatial length of the system. And also from the entanglement perspective, people begin to realize that such kind of fracton phase of matter, although some of the exactly solvable lattice models like stabilizer codes do share lots of similarities with the lattice gauge theory we already learned about, it's very different from the TQFT from the entanglement perspective, in the sense that for some fractal models which have subsystem symmetry, and we already know their ground state, they are short-ranged entangled, or at least we know there are some finite local unitary steps that can adiabatically disentangle all of the qubits. Some of them do display some those novel entanglement properties, such that if we just use the calculate the entanglement entropy and exclude the area part and focus on the non-additive part, or we use Preskill's method to figure out what they call the topological entanglement entropy. These short-range entangled states sometimes can have a non-additive, what we call fake topological entanglement entropy, which seems like a law and two correction, and it's highly dependable to a geometry cut or the way you made a cut. So that actually implies that for these fracton models, no matter it's long-range entangled or short-range entangled or not, the entanglement entropy, especially the non-additive part, which shows the intrinsic mutual information between different parts, also depend on the geometry structure of the ground state. And in addition, from the non-equilibrium side, we've already realized that because the quasi-particle have restricted mobility, they can exhibit some glassy behavior and subdiffusive dynamics. They have interesting hadron dynamical equations, and this is what Andrew Lucas will talk about tomorrow morning. And there have been a lot of challenges, like what are the theoretical framework for lots of lattice models, and how do we extend them to the continuum limit? Does the lattice model and continuum limit really match? From the experiment side, this is something I will talk about later in a moment. Are there any experimental realizations of these lattice models, and what are the thermodynamical properties or transport properties which help us to probe or figure out what are the fingerprint for these fracton phases? So among all of the challenges, because what we are focused on here is mainly about UV-IR mixing. So previously, how we understand a critical phase or just a liquid phase with quasi-long range order and power law decay correlation function is if we measure any operator or the correlation function between a 2-point or multi-point operator, we know that the operators, the correlation functions exponent is universal, that is independent of the microscopic detail of the system or the interaction. It's only dependable to the space-time dimension, to the symmetry, and to the locality of the system. And that is why in our previous knowledge on classical liquid phase or quantum liquid phase, the coarse grain always work. We can always keep the long wavelength physics as the essential description of these liquid phases, and just coarse grain out the short wavelength physics, because they live at a high energy part of the spectrum and they do not create any additional singularities. So they should not change the qualitative behavior of these exponent or correlation functions. However, what passed us is, apart from what Nati already mentioned, from my side, what passed me is from some well-defined condensed matter lattice models, which can be simulated by a variety of numerical methods like the Sine-Freeman-Monte Carlo or density matrix renormalization. We do recognize that there exists a large number of critical point, or say second order phase transition point, which turn out to be exotic. And here I only mention two examples. One is symmetry breaking phase transition. We know, like in two spatial dimension, the Yizhi model, quantum Yizhi model's symmetry breaking phase transition is well known. It's the Yizhi universality class. And now we can think about a lattice model where we have a three-body interaction with a quantum fluctuation in the presence of a transverse field. This model does not have any global symmetry because we have three-body interaction of a Z2 spin. But in the meantime, it has an exotic symmetry where we call it a fractal symmetry, such that the Z2 charge is already broken globally. But if we count all of the Z2 charge on a fractal, 2D fractal, like a 2D Sierpinski triangle, we'll figure out that the charge on these submanifold turn out to be conserved. And numerically, these models can exhibit two phases. One is a symmetry invariant paramagnetic phase, like everything is polarized in the sigma x direction. And the other is more like the fractal symmetry breaking phase. And in between them, there seems to be a continuous, or at least from thermodynamics, it's a second order phase transition. However, if we calculate the energy density correlation function, it turns out that the exponent of the power law decay correlation function is totally independent of the lattice model, the space-time of the lattice model. Instead, it somehow shows a fractal dimension, the log 3 over log 2, which is exactly the dimension of a 2D Sierpinski triangle, or the dimension of the charge conservation on this submanifold. This was verified in numerical simulations, and theoretically there have been some progress, mainly by Chen Ke Xu and Sagar Vijay this year, and they try to try to extend this model to its U1 limit, and from some fine-tune RK point, they try to figure out whether one can calculate the correlation function of the energy density and figure out whether one can approximate such kind of behavior. And honestly, even to this end, we don't have an answer on what should happen if there is a critical point, or say phase transition point, when a subsystem symmetry is broken or a fractal symmetry is broken. Is the universality just dependable to the dimension of the symmetry on the submanifold, or is it also dependable to other factors? This is something which still remains a mystery. And the second one is actually pretty well known, and Natty also slightly mentioned about it. This was first studied by Mancanti and Leon Balance, and later also studied from field theory perspective by Cenke Xu and Masu Fisher. It's a quantum rotor model in two spatial dimensions, which has a subsystem symmetry. So it's something like the Hubbard model extension, but we only have ring exchange interaction between the boson on a square lattice. And there one finds that there can support a liquid phase where the full spectrum is gapless with a huge number of singularity or gapless branch along the two axes. And in addition, when they first calculated the correlation function in time and space, the Magnon correlation function, what they find is it's exotic in the sense that if we calculate the Magnon correlation function in time, it's something like a short range correlated. It decays much slower than any power law, but still a little bit faster than exponential. However, if one calculate a higher order derivative of the Magnon operators, one can find such kind of operators turn out to be more relevant, and they show power law correlation function. So this model, lattice model, and calculation was, some of the calculation was done more than 2 decades ago. Now, at that time, it pastels a lot because they called it a sig theory or EO theory, since if usually if RG works, if an operator is irrelevant, usually the higher order derivative of that operator should be irrelevant as well. Well, first, by some simple dimension counting, that turned out to be true. And second, if we have an operator is irrelevant, then the spatial derivative of that operator usually correspond to some rough field configurations. And usually in RG, this rough field configuration should cost larger energy, and we just cost rim them out or just ignore them. So how can this happen? And now we still cannot fully answer these questions, but one thing we're already clear about is such kind of UV-IR mixing came from the fact that all of these models have a subsystem symmetry. And because of the subsystem symmetry, it turns out that the low energy degree of freedom is not just at the k=0 point or the long wavelength point. Instead, there could exist a large number of zero energy points which survive at a higher momentum. And if we write down, or if we want to plot the field configurations of these modes, those correspond to some rough field configurations in space where a field configuration fluctuates strongly in space, but nonetheless, such kind of UV mode does not cost any energy, and hence they do contribute to the low energy behavior of the field theory, and they do create additional singularities when you calculate these correlation functions. And from this UV-IR mixing, what we currently know about is there is a special type of subsystem symmetry which allows that the zero energy, the local fluctuation can also cause zero energy or low energy, and hence these low energy modes from short wavelength physics do contribute to the low energy behavior, and they're essential that cannot be coarse-grained out. And because of this UV-IR mixing, it turns out that there could exist a large number of new phase transitions or new liquid phase, which is beyond of our previous understanding. Like previously, we all feel that the critical exponent is only dependable to space-time locality and symmetry. And now we know that it can be independent of these factors, but instead it's dependable to the subsystem symmetry dimension. And hence we can have emergent fractal dimension of an operator. Even the lattice model we begin with is local and well-defined on the regular lattice. And because of UV-IR mixing, the effective field theory do depend on the UV cutoff. And hence, previously, when we write lattice models, we always assume that it should have a reasonable limit in the continuum limit because only the short wavelength physics contribute. So once you begin with the lattice models, we always assume that it has a continuum limit and all of the low energy properties or the central properties should behave the same, at least qualitatively. But in this type of model, it seems that the lattice model versus continuum limit are not totally the same. And in the meantime, when we consider something like liquid phase transitions, or if we consider the field theories of these exotic models with subsystem symmetry, it turns out that previously we just need to be careful about, like when we think about liquid phase or we think about a quantum liquid phase, whether we have a stable liquid phase or whether we will encounter with confinement or not, we just look into the instanton event. And as long as it is irrelevant, we can probably say that, okay, we have a new type of condensed matter system, which has a stable quantum spin liquid. But now, because of UV-IR mixing, it turns out that even an operator, like an instanton operator, is irrelevant. It's highly possible that those higher order operators, like a pair of instanton, which forms a dipole, or a quartet of instanton, which forms an instanton quadrupole, can be more relevant than a single instanton operator itself. And hence, it is also pretty challenging for us to claim that we can figure out an exotic quantum liquid phase, or we can figure out whether there is a fractal version of the quantum spin liquid. Okay, and finally, because Andres asked us to say a little bit about the futures, what are the future central objectives, or what are the questions I would like to see it being answered or be cleared in the next year. Well, there have been lots of questions which is not clear and turn out to be very exotic and interesting. Like there are lots of intriguing theoretical questions, like how do we classify these phases, not just by their ground state degeneracy or foliations, and how do we characterize such kind of UV-IR mixing in a zoology of condensed matter models, and whether they have a reasonable limit in the continuum limit. And so now let me talk about more about the other two aspects. Another aspect is about search for fractal physics in complex materials or synthetic quantum matters, and how do we prop them. So because as a condensed matter theorist, previously when I give seminars, mainly condensed matter seminars, the most question I receive is, yes, you show a lot of models, but whether they really exist or whether you can really make it. So recently there have been lots of interesting proposals, mainly by theorists, like Nick Shannon and also Yang King group had figured out that in some frustrated spin models in 3D, mainly like spin models on irradiated materials or frustrated spring models defined on a particle lattice, one can figure out that the local spin-spin interaction does the job like a local projection, which introduce a higher rank gauge theory structures. And as long as we turn on some quantum fluctuations, one can expect there being a fractal version of the quantum spin liquid. So this is the proposal. But what is still unclear is, first, do we really, because it's a quantum liquid phase, do we really have a stable fractal liquid? Well, in previous days, when we talk about quantum spin liquid or that quantum spin liquid is stable or not, the first thing we look into is instanton event, whether they're relevant and whether they will confine the phase. But now, because of fracton, we have UV-IR mixing. It turns out that some higher order instanton operators or higher order combination of instanton operators can also be relevant and be potentially drive the phase into a confined phase. And second is, how do we prop them? Previously, there have been some interesting proposals, like from the spectroscopy side. There are some pinch points where people can measure them via NMR experiment. And another interesting side, which still to be explored, is that because of UV-IR mixing for fracton state, we have large number of low energy modes, which is not coming from the zero momentum point. It's also coming from high momentum point. So coming from the raw field degree of freedom. And if we have a large number of zero energy states or low energy states in the liquid phase, in principle, they can qualitatively change the transport behavior. So one thing I'm pretty interested in, and I hope I anticipate someone can eventually answer in the next few years, is what are the interesting transport behavior of fracton physics and whether they can qualitatively distinguish a fracton liquid phase with an ordinary liquid phase. The third part, I believe tomorrow there will be lots of descriptions and focus discussions on hadron dynamics in fractons and the non-equilibrium properties of fractons. And apart from what they will probably mention, one thing I'm pretty interested in is that previously we already know that in fracton physics, there could be lots of interesting phase transitions because due to UV-IR mixing. In recent years, apart from the phase transition in the equilibrium sense, there are other studies on non-equilibrium phase transition, like the measurement-induced entanglement phase transitions. And people do find there is an area law or volume law phase, and there could be a critical point or critical phase in between them. And I wonder if we have a fracton system where all of the random unitary gates and all of the measurements do obey a certain type of subsystem symmetry, whether there could be an entanglement phase transition in fracton phase of matter, and if there's a critical phase or critical point between two different type of phases, whether there are new interesting physics and how are they qualitatively different from the entanglement phase transition we already know about. Okay, so that's it. Thanks.
Thank you. Well, thanks to both of our panelists for the wonderful talks. And now let's move on to questions. Do you have any questions from like the room? There's something out on Zoom. Maybe we start there. John, you want to get going?
Yeah, hi. So yeah, I have a question for Nadi. So in the same spirit in which you gave the quantum field theory panelists a hard time about not mentioning the RG, I wanted to ask about your opinions of attempts to generalize various kinds of RG to fracton models, in particular about the ideas of Xie Chen and her collaborators about trying to define what we mean by universal properties of at least certain gapped fracton phases as sort of equivalence classes modulo stacks of 2D topological order.
Okay, so you asked several different questions. Let me try. So in ordinary field theory, I think the UV to IR path, rather than the other way around, is absolutely crucial. Whenever we do condensed matter physics, that's what we have in mind. We formulate the problem with short distances. We want to see the phase, which is what happens at long distances. So, and I'm a great fan of the renormalization group with the Wilsonian effective action. I've made my living with the low energy effective action. So don't misunderstand me. And I think this is very central if we want to understand quantum field theory. To me, one of the lessons from all these exotic phases is that standard picture of the renormalization group does not work because of this UV-IR mixing. And I want to emphasize that UV-IR mixing, this is not the first time UV-IR mixing appears. We have had signs of UV-IR mixing in gravity, in various limits of string theory. As far as I know, this is the first time it happens within a lattice model, but we had a glimpse of that before, and people said, this is a warning sign for the renormalization group. In fact, in the first paper, the phrase UV-IR mixing was mentioned in print. There was a footnote saying that maybe something like this could explain the issue of the cosmological constant. And of course, there is no model or anything, but this is really big. It's very important. So the fact that there is a lattice model that exhibits such UV-IR mixing, even though the details are not the same, I think is fascinating, and it's both a warning sign to be too dogmatic within field theory, but also telling us that there's something deep we're not understanding. Now, the second question you asked, okay, so for the first question, I think the people in the field theory panel should have emphasized the renormalization group because it is central, and you don't appreciate how surprising it is when it does not work if you don't appreciate how important it is when it does work. So now going to fractons, I do not know what to make of it. I think this is something big that needs to be understood. I am very sympathetic to Chia's and her group attempts to have a variant of the renormalization group where you perform a renormalization group transformation and decouple some modes at the same time. It somehow has the right flavor and it works in specific models. So that's why I think it is very exciting. And maybe that's the right way to proceed. I'm not sure. There is one aspect of it which is inevitable, which is really a challenge to whatever you do, and that's the final answer depends on the UV data. That's so forget how you did the renormalization group, forget how you got from the UV to the IR. The final answer is sensitive to the UV data. And if you track what it does in their approach, is that these decoupled qubits are doing the job. So they give you the extra ground state degeneracy because you kind of manage to disentangle them. Now, I do not know whether this is the approach that will eventually crack the problem. Personally, I believe that it was important for them that this qubit was exactly decoupled, and it was decoupled in a non-local way. So it's not one qubit associated with one site on the lattice. This qubit is sort of kind of spread all over the lattice. It's a non-local transformation. Personally, I believe that it works the way they did in models with foliation, but in models without foliation, like for example, Haas code, I do not know whether such a thing was done. Maybe it was done and I'm not aware of it. I believe it will be, even if it's possible, it will be a lot more complicated. And we can imagine that there are other models that are even crazier than that, and that approach would not work. So this is a general essence here. Since we are kind of pushing the envelope, we might make progress in some models where the subsystem symmetry is relatively simple, but we shouldn't fool ourselves to think that that will solve all the problems, because sometimes it's much more complicated.
A small comment. So actually, Ha himself did an analog of this sort of RG in his qubit code.
He did. Okay, good. Thank you.
And the story is that it's sort of self-reproducing. That in order to make a copy of his code at system size 2L, you need. Sorry, it's not. So first of all, it's not foliated. You have to enlarge it in all directions at once. And in order to make a single copy of the system at size 2L, you have to start from a copy from essentially 2 copies of the system at size L. So yeah, so I don't know how to think about it in the same terms as the foliated.
But I think what you say is really underscored what I said. When there's foliation, it's subtle. When there's no foliation, it's more subtle. And for all we know, in other models, it's even more subtle than that. In fact, I'm writing a paper with my 3 co-authors who should be in the room now. And we have another model which is also kind of crazy, like house code. And I do not know whether a prescription like that works there. It would be interesting to check. But the thing is that the number of examples, you can count them on one hand. And you try to make a classification. If you have 5 fingers, you'll say that there are 5 types. Yeah, this is clearly premature. And I believe there are many other examples, and maybe they have different features.
Yizhi,
Thank you for the comment.
I was just wondering whether Yizhi has something to add other than that. Shuheng had some comments. different questions. And Yizhi, did you want to add something about the RG flow? Or
No.
okay, then let's have Shuang ask the question.
What's the status of robust quantum memory, which was one of the early motivation for fracton phase?
Are you asking me?
It's probably either one who has, anybody has something to say.
Since the question came from Shuheng, I don't think I can say anything that Shuheng doesn't know. In fact, most of what I said today, I learned from Shuheng.
So actually well, what I can say is pretty limited because what drives hard to study such kind of exotic code is that if we want a quantum memory, if we want a quantum stable quantum memory, probably the quasi-particle cannot be created by any string operator. So even you have finite temperature and thermal fluctuation, it shouldn't take a short time to change the local spin qubits because for string, if the quasi-particle is created by string operators, then actually once you create a pair of quasi-particle wind around in a non-controllable loop and goes back into itself, it only costs finite energy. And hence what you talk about is probably we need energy barrier like this first 17 hard code, which is created by fractal operators. And once you enlarge the fractal operator from one size to the next size, you have to go through intermediate steps, which cost that energy. But nonetheless, the energy it costs is still logarithmic compared to the fractal size or the system size. But for a true robust quantum memory, what you want is the energy cost must be at least larger than the logarithmic behavior. So for Haskell, it's something like has a glossy behavior, but still not fairly enough for the robust quantum memory. But honestly, if you just want something like a measurement based quantum computing, or you want a robust quantum memory, there are other ways one can do that, which is not that hard. Well, theoretically, it doesn't seem to be that hard, but I'm not sure experimentally it can be controlled. Like if you just have some random disorder like NBL for a 2D Tauri code, then probably this could be a robust quantum memory. So honestly, what I can say is pretty limited on that.
Yael, do you want to pick us somebody from the Zoom?
Yeah, I think Tarun is next. Please go ahead.
Thanks. Yeah, I had maybe a few things here. So the first question was actually completely I had three completely different things. I don't know whether I should take all of them, but one question is a bit random. Is about so I would say the two most famous regularization schemes in condensed matter. The two most well-known one are lattice. The other most well-known one is Landau level quantization. Landau level regularization. If you put a system in a magnetic field, even if it's in a continuum, you have finite Hilbert space because of this, the way quantization works. So the question I have is, are there examples of this, whatever we are calling UV-IR mixing with Landau level quantization Landau level regularization in because in 2D also we have, these systems as you just discussed with, I don't know, this Permakanti model or whatever. There are many models. So okay, that's one question. Let me keep moving to the other question. So the other question I have was, at least at a very naive level, when we have these dispersion which looks like, let's say, sine kx times sine ky, which has the zeros and on kx equal to 0 and ky equal to 0, the energy is 0. At least at very naive level, it resembles like a Fermi surface. Are we saying that even like a standard Fermi surface has UV-IR mixing? Not, or answer is yes or no, or if the answer is yes, then can we learn something from Fermi surface RG to carry over? We know that it has similar, it has this branching mirror, this idea that if you combine, if you try to do RG, you self-replicate from a branching mirror point of view. So that's a bit like Haas code, even Fermi surface in that very core sense. Okay, that's second question. Third question was just about quantum memory, I think I'm not sure about the. I think we have so far no model of any kind which shows finite temperature quantum memory in less than 4 dimensions. That's my understanding, including disordered systems.
Mm.
If you have a higher form symmetry in 3D, you can actually impose a quantum memory. This is recent work by Sam Roberts and company. So in 3+1D with a higher form symmetry, with a one form
symmetry is
symmetry.
very unnatural in the sense that I'm allowing you to break all. The condition I want to impose is that there exists no symmetries in the system, including any.
Yeah, then there's no examples, right?
Yeah, that's how we think about topological order generally, right. Break all possible symmetries, and then only locality is the only principle. So then there's this work by Michel, and I'd heard there's some codes on defined on some fractal lattices, and those are the ones which I think probably are the only thing which seems have something to it, but I think people haven't studied them in a careful way, and what are their properties, but if you go beyond local systems that allow k local systems, then of course there are examples perhaps, but that's going too far. Anyway, yeah, so my questions were about the other two things. Sorry.
So if I can try at least some of them, I think I can say something semi-useful. You mentioned the Landau level and the Fermi surface. Both are characterized by having in the continuum a large number of low energy states. I'll say that more precisely. The Landau level has a finite number of states, and we can make it very large, and they're all degenerate. And you can ask, is this an example of UV IR mixing? And I'm not sure how to answer this question, but you're right, there are a large number of states, but typically a small perturbation removes that in a way that we fully understand. Of course, this is a big topic, but what happens there is that as we reduce the magnetic field, the number of states gets smaller, and as the number of states gets smaller, it looks more manageable. And what that really means is that it's not there are many states, but it's not sensitive to a UV cutoff. So I think I said that in a garbled way. Unlike the examples of fractons, the case of Landau level, there are many ground states. If we just think of free fermions in the magnetic field, but there is no UV cutoff that enters the problem. There is the phenomenon, there are many states, but there is no UV cutoff in this case. The case of the Fermi surface is much more interesting. And there is a way to do the renormalization route. And it was initiated by Shankar, and the version that I like is the phrasing of it a la Polchinski. The Polchinski rephrased it in a beautiful way, and it does fit the Landau picture. What is complicated there is locality on the Fermi surface. This is not what's not standard. And indeed, it's known that except in special circumstances, the theory of small fluctuations around of the Fermi surface is not captured by a local quantum field theory. But from a low energy field theory perspective, this is not as bothersome as the situation here, because we're not talking about the vacuum. We're talking about very excited states with lots of fermions. It's true that we expand around the state with lots of fermions with chemical potential, but a traditional quantum field theory says we work in the vacuum, small number of fermions, let them interact and see what they do. I'm not sure whether this is an excuse, a valid excuse or not, but it is a distinction. Having said that, I think trying to understand an effective description of low energy fluctuations of the Fermi surface in the language that is close to quantum field theory, I think is a worthwhile thing to do. And recently there has been some efforts in this direction. And personally, I think that we haven't heard the last of it. I hope I addressed the questions.
Yeah, I think I sort of understand, but I would say that even in a Fermi liquid, we are not looking, the total number of fermions doesn't matter, but you can still talk about number of quasi-particles can be small density, right? That's what random Fermi liquid theory does. It's not necessarily about what the total density is. It's more about how many quasi-particles you're exciting. Also, about the first thing I was
description. This would be the effective description, but the microscopic description uses some chemical potential to put in a lot of particles. So in that sense, if you have a small number of particles, you just add them for any finite number of particles. You still have a large degeneracy, but this is the degeneracy that we understand. The surface is much murkier. The point in both cases, free theory is fully understood. And if there is a description in terms of quasi-particles, we also sort of understand that. But once we start adding interactions, I'm not a condensed matter physicist, so I don't know, but my understanding is that at least, except in special circumstances, the low energy excitations of the Fermi surface are not captured by a local quantum field theory. There are more experts in the audience than people who know much more than I do about the subject, but I think this is a correct statement.
Okay.
In one spatial dimension, there's an exception.
Sure.
But in five spatial dimensions,
thanks.
If you look at the Shankar renormalization group, it is all done in momentum space.
Right. Yeah.
But it's not done in coordinate space. So if you want to have an effective theory in space-time with some coordinates in space, there isn't a satisfactory theory. I've seen recently some attempts to do that by covering the Fermi surface with patches. I think Subir and his collaborators work on it, but I do not know if there is a satisfactory description which gives the entire Fermi surface rather than patch by patch.
So, did you have a comment on?
Yeah, so actually I have one comment. In condensed matter literature, the first acronym of UV-ion mixing was probably used in 2D or 3D Fermi surface. Like last year, I remember Sun-Sek Lee and his collaborator has an interesting work on UV-ion mixing phenomenon in Fermi surface and their various instabilities. And they're actually one of the protocol they adapt is pretty similar to how we deal with the lattice model of the U1 version of the Plaquet-Yizhi model. For Fermi surface, they begin with something like Malinsky or Subir's patch theory, and for each patch, when they do the renormalization, it's something like shell renormalization, where you go through the tangent directions, but don't renormalize along the parallel direction, so you will not include or exclude additional zero energy mode or the length of that framing patch. And same like when Xu and Fisher deal with that U1 version of the Plaquet-Yizhi mode, especially in the liquid phase, when they write them in the dual theory and see whether that vertex operator or winding number is relevant or not. What they do is they only do a coarse-grain along the tangent direction, which is tangent to the zero energy branch along the two axes, and hence when they count the dimension of an operator, like they count the dimension of a dipole operator and see whether it's relevant or not, they will constrain the space-time in a 1+1D space-time that is perpendicular to the dipole. It's something like a 1D stripe, and only look at the renormalization of this 1D stripe. This is how they figure out whether there are operators that are relevant or not, and what are their scaling dimensions. But the issue is from some simple model, especially subsystem symmetry with straight line-like symmetries, this is something we can adapt. We can just use the protocol they already developed in a Fermi surface theory. However, lots of fractal model, especially the initial fractal model, like what Ha proposed, it's on a more exotic manifold, like charges conserved on fractals or on a more complicated sub-extensive manifold. And for such kind of complicated manifold, like for the Newman-Moore model, where charges conserved on a 2D fractal, we know there should be some UV-ion mixing, because as long as you have subsystem symmetry, there should be some low energy mode that is contributed by the UV physics or by the short wavelength physics. But we at this point, we don't know whether there is a reasonable renormalization group or similar renormalization group scheme we can adapt in these type 2 cases.
Thank you.
Let me take a comment about what you said. First, about the origin of UVIR mixing in some of the early examples, and this is field theory in non-commutative space. I think it was even before the Paramakanti paper. We talk about
So I say condensed matter, only in condensed matter.
Yeah.
The first
So, and the picture there is actually very suggestive for the picture of fractals. What happens there is that the fundamental degrees of freedom are scalar fields, but they behave like dipoles. And what happens to the dipole is as you give it high momentum in the x direction, it grows in the y direction. So as the dipole moves with larger and larger momentum in x, it becomes physically bigger in the y direction. So the UVIR mixing comes from the fact that high momentum in the x direction has consequences at long distances in the y direction, which is very similar to what we see in the examples of fractons or in the example of the Paramakanti et al. The details are, of course, different, but the UVIR mixing arises because of this phenomenon of the growth of the dipole. The second comment I want to make is about the discussion of relevant versus irrelevant that appeared both in Yizhi's talk and in the comment she made now. When we discuss whether an operator is relevant or irrelevant, what we usually ask is, what is the dimension of the operator? In fact, Yizhi also said that both in her talk and in the comment now, is what's the dimension of the operator? In order to make the dimension of an operator well-defined, the theory should be scale invariant. You cannot discuss the notion of dimension in a theory which is not scale invariant. The model of Paramakanti et al. Is not scale invariant. In fact, if you write the Lagrangian, that you look at the Lagrangian that you wrote, Yizhi, the Lagrangian that Yizhi wrote in her slide, that Lagrangian is not scale invariant. It's not scale invariant because phi has to be 2 pi periodic. If it's not scale invariant, we cannot discuss the notion of dimension. And indeed, the correlation functions in these models do not exhibit scaling behavior. That's why the model is so puzzling. So on general ground, before we get into relevant or irrelevant, this is too specific. If you don't have scale invariance, you cannot discuss dimensions of operators. The last point I would like to make, and since again this was brought up, Yizhi wrote a Lagrangian with a parameter k. Question, is k finite or is k infinite? Answer, if when you write the continuum Lagrangian with a parameter k, you assume that the parameter k is finite. If you want this lattice model to have anything to do with this continuum Lagrangian that you wrote with finite k, then you have to take the limit that we called the continuum limit, which is different than the thermodynamic limit. So we have been criticized by many people, oh, you take the wrong limit. So first of all, we didn't take the wrong limit. There are many limits and all of them are right. But the limit that we were interested in is precisely the limit that condensed matter people were interested in. In particular, this is the one that appears on the slide. And in that limit, the low energy theory is not scale invariant. This is absolutely important. And I think it's important to keep that in mind, especially when we discuss issues of UVIR mixing.
Any more comments on this, or should we move on to the next question? I have at least one more question on Zoom, one in the room. I would be tempted to go back to the room for now.
So I have a question about UVIR mixing in these fracton models. Is it too naive to think that a lot of this UVIR mixing is largely a consequence of an inequivalence between low energy and low momentum or long wavelengths? Because that is, for example, to relate to the Fermi surface discussion, that is roughly what happens for Fermi surfaces. Their low energies and low momenta are not the same thing. Is the same thing what happens in fractons as well, or are there examples where it goes beyond that?
Your comment is well taken. I think it's crucial that it's in the right direction. That's why it's hard to find it in relativistic theories. Although, first of all, I'd like to add parenthetically that in models that come from string theory, come under the name of little string theory, we see UVIR mixing in relativistic systems. So putting that aside so that we know, that's the most enigmatic theory I know about. Any model of fractals looks completely trivial compared to the subtleties there. But if we go back to more down-to-earth examples, which are non-relativistic, the comment about low energy versus low momentum is well taken, but it's still puzzling because when we want to do coarse graining, we always think that coarse graining goes simultaneously. We remove high momentum, and by doing that, we remove high energy. That's not the case here, so something will have to give. And maybe, as John brought up, we have to use this procedure of Shia and her collaborators of gradually peeling qubits. Maybe we need to do something else, but I don't think it's clear. And I think this is a very important question that needs to be addressed. I find it really suggestive that the issue of UVIR mixing, and more generally, the fact that the standard renormalization rule picture does not work, hits us from many different directions. It's not just one example, it hits us from many different directions. I personally have been obsessed with it for some 25 years or so in various contexts, and I really don't know what to make of it. I used to dismiss it, but I think it's time to really face it head on. It's trying to tell us something.
I'm surprised that you didn't mention black holes.
I did mention it. In all of my talks, I always say in black holes, when you throw something in, you try to explore it at short distances. You go to high momentum, high energy, and then what happens is the black hole grows. And by doing that, it shields the short distance physics. But then you could say, this is a theory of gravity. We're doing a theory without gravity. So the notion of distance is more well-defined. So people use the black holes and related to that T-duality, which also has UVIR mixing. These two are characteristics of theories with gravity. They have black holes, they have T-duality in the context of string theory. And we see from that the UV and the IR mix, but the response is, yeah, space-time is not meaningful. The reason we have T-duality is that space-time is not meaningful. We shouldn't even be discussing short distance and long distance because in which metric and so forth. The same thing is true about black hole. Space-time is maybe emergent. Maybe we need new ideas about space-time. The common thing in all the other examples is that space-time is given. There's a rigid, well-defined space-time. We know what distance means. We know what energy and momentum means. And yet we face the problem.
Yizhi, did you want to add something?
Yeah, so actually, for UVI mixing here, what we mean is that the low energy degree of freedom came from in momentum space UV, where we have high momentum modes or raw field configurations, which contribute to the low energy part of the spectrum. But another question is because for fractal models, this is very common or this is expected, since as long as you have subsystem symmetry by symmetry, once we have a smooth configuration which doesn't cost any energy or cost a very small energy, we can always do some subsystem transformation to this mode. And a subsystem transformation after a smooth mode would usually be a rough mode, but since they are related by symmetry, they should share the same energy. That's it. And another question is it possible that we don't have a subsystem symmetry, at least in the UV level, like in the Hamiltonian level, but we still have UVI mixing, or we still have a similar phenomenon? Actually, again, Fermi surface probably could be an example. And the one reason for that is because there have been some recent proposals of claim that in 2D Fermi surface, actually, each patch has a emergent symmetry. So it's more like a LU1 symmetry. They could have some emergent, something like the emergent subsystem symmetries. And also in some frustrated spin models, it could be possible that the UV Hamiltonian doesn't have such kind of symmetry, but the low energy degree of freedom turn out to have a larger symmetry, like have a subsystem symmetries, and those weak subsystem symmetry breaking terms turn out to be irrelevant. So another direction I think people are pursuing, like the UC and Barbara group are trying to pursue, is whether we can have UVIR mixing in non-fracton systems or in some specific lattice models where the subsystem symmetry is not explicitly presented. Yeah, this is just my naive understanding of that.
Shagong Wen has been waiting very patiently for a long time, so maybe it's your turn finally.
Yeah, I like to mention maybe there's another angle to look at the renormalization group flow of a fracton phase. One point is that the existence of a fracton phase in three-dimensional space seems is very much related to the existence of a non-invertible topology order in 2 dimensions. So there's we have a stacking those layers of topology in 2 dimensions, and the anion in each layer cannot tunnel, and that's led to this emergence of a subsystem symmetry. Even though at the beginning you have no symmetry, but this in two-dimensional long-range entanglement can lead to this emergence subsystem symmetry. And but this picture really in line with its foliation picture, and seems suggests some kind of reverse renormalization. You know, once you have some kind of intrinsic foliation of a space, then one may want to do the RG, which is try to make a foliation spacing bigger and bigger. And so although in the whole system there's a many foliation, but we may also have a limit where the foliation have a large separation. And that's give rise to some kind of universality. So basically that expose this entanglement pattern in each layer. And so the layer may intersect. So this is a stratification picture. And so that led to some kind of understanding, RG understanding, using this what they call reverse renormalization. And so this yeah, this is just another angle to look at this problem. Yeah.
Did any one of the panelists address this, or you? Otherwise, I can take the next question, which is like Son had a question.
It's more like one comment and one advertisement. So the advertisement I'm going to put in Zoom. The comment is the following. People have mentioned system with in the magnetic field and Fermi liquid as 2 system with IR UV mixing, and there may be a relationship between them which arises in the context of the fractional quantum Hall effect. We know that if we take a system at a finite magnetic field, then one can dualize the system and make it into a happy Landau level. Happy Landau level is dual to a Fermi liquid where the number of fermions is equal to the number of, is proportional to the number of flux quanta in the dual description. So I'm not sure if there is any insight one can get on UVIR mixing by using the fact that these 2 systems are dual to each other.
Yeah, actually, I have a question to Son, because you mentioned that Landau level. I remember you probably not this reference you sent in the chat, but earlier people was still on the projected half-U Landau level, where claim there's something like a fracton behavior, because for projected half-U Landau level, you can describe the Fermi surface in terms of a Dirac spin-out at finite chemical potential, and their Dirac spin-out came from the fact that after Landau level projection, the flux attached to the electrons are slightly shifted, and from the projection, you can see that shifting direction, more like a dipole because it carries charge and anti-charge, is perpendicular to the momentum. That's the momentum of the composite fermion on the Fermi surface. So it's something like I have a dipole in one direction, and the momentum is always transverse to that. It's something like in the IR level, it's something like a dipole can only move to the perpendicular direction to its orientation. And I wonder there, because again, once you have a Fermi surface like the half lambda level, you do have UV mixing, but is there any intrinsic relation with the is there any relation with that such kind of dipole lock-in or emergent fracton dynamics and the UV mixing in the Fermi surface you described in the half lambda level?
Can I answer? Yeah, so the notion that the quasi-particle, the composite fermion in the half lambda level has to have a dipole moment comes back to work by Nick Reed already in the 1980s, late 1980s. And here the picture is very simple. You have you can show that composite fermion carrying momentum K has to have dipole moments that proportional to K. So one can think about that as a particle and a quasi-particle and quasi-hole separated by an amount equal to K. And here you see that if K goes to infinity, the size of this dipole goes to infinity as well. And so maybe that's related to the issue of UV-IR mixing. You try to go to UV, taking the momentum of that quasi-particle is to infinity, but at the same time, its size blows up. Yeah, so becomes large.
Yeah, maybe. Oh yeah. So the comment is probably related to this one. So is it correct that this feature of dipole locking to the momentum is just a result of lowest lambda level projection, and it applies to the entire Hilbert space, nothing to do with whether we are in the composite Fermi liquid phase or not, right? And that question following this is that, does this fracton-like feature, does it have any implication on dynamics in the lowest lambda level?
Yes.
Okay.
Yes, but it's all no.
It's all no.
Yeah.
I see. Yeah, and sorry, one more question. Sorry. So this is back to the RG question that had been discussed for a while. So many comments refer to the theory where you have, say, a line of low energy modes, in momentum space, like Fermi surface or some of these exotic theories. However, there are also exotic theories, for example, like a Lifshitz model, where it's only gapless at one point, but still has some exotic behaviors. So I'm wondering whether the RG is well understood there, without the complication of having, an extensive number of gapless points. Did one of the panelists want to say something about this?
I think that my collaborators will be able to say something useful about Lifshitz theory.
Well, we have them here since we are kind of already 20 minutes over. Maybe we take questions to the panelists rather than questions to the people here, since we're going to have informal discussions anyway, then we can bug your collaborators forever.
Yeah, actually, for Lifshitz theory, do you just mean that the dynamical exponent is not one? Like z equal to Lifshitz theory or something like that? No.
Yeah, and that tells you that there are more states at low energy than you would expect.
Yeah, because for Lifshitz theory, I think the exponent would be different because it's more like a dynamical exponent would also correct the critical theory, since the density of state at low energy is different. And here it's a similar origin. The density of state at low energy is different from relativistic theory, but it's not just a small correction. It's more like a sub-extensive that is spread throughout the high momentum region, and hence it could be sensitive to UV cutoff.
Yeah, and I'd like to add to it also that when people say Lifshitz theory, they really mean two different things. Sometimes phi is a non-compact field, and sometimes it is a compact field. This is a question that came up during a SONS talk this morning. And when phi is compact, there are many of the subtleties of UVIR mixing arise through these funny ground state degeneracy and so forth, associated with the linear slope that he used in his talk, that you can shift phi by a term linear in X. You have to do it more carefully when to see what the boundary conditions are and so forth, but it does lead to peculiarity in the ground states associated with peculiar symmetries. And the symmetry does depend on the UV details. So already Lifshitz theory, if you just say that phi is identified with phi plus 2 pi, already has many of these subtleties. I hope it addresses Monk's question. I think it was Monk who asked the question.
Monk asked the question. Yeah. Did you want to say something else? I'm tempted to say we kind of end with one more John McVitie question. He asked the first, he asked the last, and then we are done since we're 20 minutes over.
Okay, thanks. I have a somewhat speculative question based on Yizhi's observations about the phase transition of the quantum Newman-Moore model.
Mm-hmm.
Do you think that there's a generalization of the epsilon expansion, where instead of varying the number of space-time dimensions, you vary the dimension of support of the symmetry? The fractal dimension of the symmetry operators?
Yeah, in principle, one can do that, but for epsilon expansion, usually we begin with a dimension. Which can have some perturbative expansion, or at least have some small parameter to do a perturbative expansion. And here, the problem, we have two problems. And first, even for that model, we don't know which epsilon equals 0 condition shall we begin with, which has which is well understood. And second is, previously we just assumed that the dimension is 2 plus epsilon and see what would happen. And although we don't know what's the physical meaning of that, but mathematically we can do that. And here, if we want to say that we have a fractal dimension, which is like log 3 over log 2 plus epsilon, even mathematically, I don't know what does it mean. You can say that it means that the charge is conserved on the special manifold that is conserved in a special manifold, like a fractal plus epsilon, or it's a fractal which has such kind of weird dimension. But does this model, does such kind of lattice model really exist, or do we really have a small expansion which can connect the Newman-Moore model to the X plus epsilon model? Honestly, I don't know.
I think even in the case of the ordinary epsilon expansion, we don't know a family of lattice models of every fractal dimension, right? Mm-hmm. Like in the paper that Nadi just posted to the chat shows that some things are shared by putting the model on a fractal.
Yeah,
right?
Yeah, but they're actually for like 2 plus epsilon, you know that it's something like the dispersion of the low energy density of state. We just tune it by epsilon. But here for this model, because it doesn't have a reasonable continual limit, so we don't know what are we know there are a large number of low energy states which survive at a high momentum, at least from the dynamical structure factor one can observe. But theoretically, we don't know where do they exist and how do we characterize them, like where they are in momentum space and what are the dispersion if we just do small p expansion. And based on that, we still don't know if we have a plus epsilon expansion, how does it correct the low energy dispersion or the density of state?
Okay, thank you.
Yeah, I would be tempted to say we are done, but Yale has his hand up and I should never ignore my fellow organizers. So,
No, I apologize. Maybe I shouldn't take more time, but I had a very naive question that just came to mind. So, of course, it's well known that the lowest Landau level exhibits coordinate non-commutativity. From that point of view, is there any manifestation of the UV-IR mixing that occurs in non-commutative field theories in the lowest Landau level, or is this not relevant?
It is relevant, and it was discussed in detail in the high energy literature in the early 2000s. So in the early 2000s, maybe end of 99, maybe 99, I don't remember the exact date, people were interested in non-commutative field theories, and people immediately saw the connection with physics of the first Landau level. I think this connection was first pointed out by Lenny Susskind around 2000. Maybe I'm off by a year or two. And it was discussed in the thousands of papers, maybe I exaggerate, but many hundreds of papers addressing it. And it's really the same physics I described earlier, that as you pump momentum in one direction, the system grows in the orthogonal direction.
Okay, thanks.
On that note, I would think we should thank our panelists.
I should also add, I'm sorry, that Senthil was also interested in this particular question recently. I do not know whether there's a paper or not, Senthil and his collaborators. So that's within the condensed matter community.
Thanks.
Let's thank our panelists, and thanks for sticking around with us.